All right, so let's get into some examples. We got a lot of them, but we'll start off with some fairly basic ones. So in this case, I have the sine of x. I'm sorry. Yeah, that's supposed to be an x. Got to forget that. So I have the sine of x times secant of x equals the tangent of x. Um, so again, we want this side to make sure it looks like tangent. So I think the easiest thing in this case for me to be able to do is just to rewrite secant in terms of its reciprocal identity, which is 1 over cosine. So I have this as the sine of x times, this would be a 1 over a cosine of x. Now you can see I can multiply, I can rewrite sine of x as sine of x over 1, multiply straight across, I get a sine of x over a cosine of x, which we know is just equal, using the quotient identity, is going to equal to a tangent of x. So a lot of times when I work on that one right-hand side, whatever side I pick, I just use equal sign to not always have to rewrite the other side. And then I just show a little question mark. It's not really mathematically correct on this, but it's just kind of the pattern that I developed through many, many years teaching this. All right, the next one, we have even odd identities. So we got to make sure we remember our identities. Obviously, we have two identities here. I think it's easiest to rewrite these. We'll do one identity first. So remember, when you are dealing with the even odd identity for cotangent, that's going to be a negative cotangent of x, and that's going to be times sine of x. Now, again, thinking of like I have two functions, I need to like eliminate this. So I'm going to rewrite cotangent as a cosine over sine. So I have a cosine of x over a sine of x times a sine of x. Again, that's sine of x over 1. So again, using the division property, those are going to divide out, and I'm just left with a negative cosine of x. You can see, voila, we now have it verified. All right, now we got the easy ones out of the way. Let's have some fun. So the one thing I want you to think about, whenever you have like parentheses and you have a trigonometric function outside of it, think of applying multiplication, right? Just like if I said, like if I had something like this, 3 times x plus 2, what comes to your brain? Immediately, distributive property, right? So here, ladies and gentlemen, we can do the exact same thing. Multiply this sine of x times everything. There's no multiplication over here on this right-hand side. So we could work on the right-hand side, but in my opinion, it's a lot easier to get rid of parentheses by applying multiplication than to create parentheses by factoring out a term, right? So if we apply multiplication here, I'm now going to get a sine of x times a cotangent of x, and that's going to be plus a sine of x cosine of x, and then tangent is going to be a sine over a cosine. So there'd be a sine over a cosine of x. Okay. Now let's see here. Those cosines divide out since that's separated by multiplication. This cotangent I can rewrite as a cosine over sine. So I have a sine of x times a cosine of x over a sine of x, and that's going to be plus a sine squared of x. So again, those are going to divide out, and I'm left with a cosine of x, right, because that's over 1. Cosine of x plus a sine squared of x, which, ladies and gentlemen, is exactly what I have here on the right-hand side. So we are good to go, verified. Now that's the distributive property. Remember, when you have a binomial, we think about FOIL, right? Binomial times another binomial, think of FOIL. You could do first. So 1 times 1. And obviously, it's a lot easier to multiply FOIL than try to create FOIL, right? Which would be factoring like a trinomial. So if we did FOIL, first times first is going to be first. And then we did outer times outer. So 1 times cosecant is going to be a cosecant of x. And then we did inner times inner. So negative sine of x times 1, which is a negative sine of x. And then we did last and last. So that'd be negative sine of x times a cosecant of x. So we have a negative sine of x times a cosecant of x. Whew. Okay. Now, what do I know about sine of x times cosecant of x? They're reciprocals of each other, right? So that's going to go ahead and subtract it down to 1. So I have a 1. See, that's going to be a 1 plus a cosecant of x minus a sine of x minus a 1. Okay. Now, in this case, the 1 minus 1 is just going to go to 0. And then you can see, again, we have cosecant of x minus a sine of x. And that's exactly what we have here on the right-hand side. All right, the next one. So in this case, this next one, now we don't really have any operations. We could look out to the left-hand side. We could look into the right-hand side. But we see something squared, right? So we have cosine alpha squared, cosine, oh, those need to be changed. So that's a cosine squared of alpha, sine squared of alpha, and equals a 2 cosine squared of alpha minus 1. All right, so when I'm thinking about my Pythagorean identities, notice on the right-hand side, I only have cosine, right? So thankfully, since I know my Pythagorean identities, is there a way for me to rewrite my sine squared so that it's in terms of cosines? Because then I could combine it. And yeah, if you think about your identities, let's use alpha because that's what's in this problem. Cosine squared of alpha plus a sine squared of alpha is equal to 1. So if I rewrite sine or sine squared as a 1 minus cosine squared, I can actually simplify it. So let's go and do that. Let's go and rewrite that. So cosine squared of alpha minus, now again, what I'm doing is I'm going to subtract the sine to both sides. So that's going to be a 1 minus a sine squared of alpha. Now I can distribute this negative. And what that's going to give me is, oh, sorry, that's a cosine. Geez, come on, Mr. McLogan. That's a cosine squared of alpha, right? So that's going to be cosine squared of alpha. Now distribute that. You get a cosine squared of alpha minus 1 plus a cosine squared of alpha. Now we can combine those, right? And x squared plus x squared is 2x squared. So cosine squared plus cosine squared is going to be a 2 cosine squared. So I'll have a 2 cosine squared of alpha, and then we still have that minus 1, which you can see, guys, now the left-hand side is equal to the right-hand side. All right, the next one. So this one, now we have a subtraction of trigonometric functions and a multiplication. Again, the more difficult side, I would say, is still going to be the left-hand side. Now, again, the left-hand side is not always going to be the side. I believe I have a problem in here where we're going to work on the right-hand side. But the point that I want to make to you is it's a lot easier to combine or add or subtract functions than it would be to create a subtraction or create an addition, right? Now, you might recognize and be like, well, Mr. McLogan, it's a lot easier to multiply these. I agree. But it's a lot harder, though, to create this subtraction sign, right? That would be actually separating them out, decomposing this to subtraction. Now, we know we can't subtract two functions from another. But we do know if we convert things to sines and cosines, that's going to create fractions. And we can add fractions by getting common denominators. So if I take cosecant and I rewrite this as a 1 over a sine of beta, 1 over sine of beta, and that's going to be minus a sine of beta. Now again, I don't have a common denominator, right? But I know I can rewrite sine as sine of beta as sine of beta over 1. Now I have a fraction minus another fraction, but I got to have common denominators. Well, what would be the common denominator between a sine of beta and 1? It's going to be a sine of beta. So what I'm going to have to do is multiply by the sine of beta on the top and the bottom over here. And what that's now going to produce is a 1 minus a sine squared of beta all over a sine of beta. Sine of beta. There you go. Okay, now it looks pretty similar, but we're not there yet. Now again, going back to what I have over here, what is 1 minus sine squared of beta? Again, it doesn't matter if it's alpha, theta, beta. If I take a sine squared over here and I subtract it on both sides, I get cosine squared of alpha is equal to 1 minus a sine squared. So this, ladies and gentlemen, is equal to a cosine squared of beta all over a sine of beta. Now again, it looks very similar. Actually, it doesn't look anything like this. So how the heck are we going to go ahead and get exactly what we have over here? Well, what I need to do is understand that cosine squared of beta is the same thing as a cosine of beta times a cosine of beta. That's all over a sine. Oh man, that's my marker. That's all over a sine of beta. Okay, so now what I can do is I can group these two together because since things are not separated by addition or subtraction, I can just say sine of beta only needs to be divided by over here. And what that's going to give me then, cosine over sine, we know is a cotangent of beta. And that's going to be times what's left over, which is a cosine of beta, which, ladies and gentlemen, is exactly what we have here on the right-hand side. All right, now we got some fractions. All right, some good old fractions. Well, you know what? Before this, I recognize, what do we know about tangent of y times cotangent of y? They're reciprocals of each other, so this is actually kind of easy. So I know that's just going to multiply to 1, right? So I don't need to do anything crazy over here. Cosecant of y. Now, if I want to get rid of cosecant, right? Because I need to get to sine. So I need to get rid of this cosecant in the denominator. So what do? If you want to get rid of something in the denominator, you multiply by its reciprocal, right? So if I multiply by a sine of y on the top and on the bottom, that's now going to give me a sine of y, and that's going to over to 1, which you can see, ladies and gentlemen, is exactly what I have here, sine of y. All right, next example. Again, I would rather, now in this case, this one's kind of interesting because remember, a lot of times I say like it's a lot easier to get rid of your subtractions. In this case, it's actually a lot easier to create them because I have a fraction already here. And what I immediately just kind of see, and again, this comes into practice of working through these problems and seeing these techniques. If I have 1 minus cosine of x divided by sine of x, yeah, I could rewrite these in terms of sines and cosines and combine them, and I bet I would get this over here. But if I look on this left-hand side, I also recognize, kind of like what I did over here, up here, how this cosine, where was that? Oh yeah, this sine only divides in over here, right? Because they're separated by multiplication. When you have terms, though, where they're separated by subtraction, then you have to take this sine of x and divide it into both of those terms. So I can rewrite this as a 1 minus a sine of x minus a cosine of x over a sine of x. And that's exactly the reciprocals of those two. If you were to write those as reciprocals and try to add them together, that's exactly what you get. Now you can see, using the reciprocal identities, 1 over sine is going to be a cosecant of x, and cosine of x over sine of x is going to be a cotangent of x. You can see, voila, it is now verified. Whew. All right. This one looks pretty difficult. I don't know if I like this one. So there's a couple things I'm thinking about here. This has a lot of functions. This one does not. This one has secant and cosecant, secant and cosecant, but it's the same thing over and over again. So how can I create? Is there something I could maybe, I don't want to add these, right? Because that secant is 1 over cosine. This is 1 over sine. I do know that tangent is sine over cosine. So if I multiplied, so this is 1 over cosine. If I multiplied by a cosine, that would work, but then that'd be, yeah, if I multiply cosine, then this would be a cosine over a sine. That'd work, but then let's get that to be a 1. Well, let's go ahead and multiply it out. Let's go and try some things, right? I don't remember. Let's go ahead and try. So if I multiply by cosine of theta, I'm just going to try something. Let's multiply by cosine of theta. That's going to at least simplify these. I know I don't want terms in terms of secant and cosecant. I need to get rid of them. So let's go ahead and multiply everything by cosine. I don't know why. It could be cosine or sine. Doesn't really matter. So in this case, I'm going to get a 1. Cosine times secant is 1. And cosine times cosecant, cosine times cosecant is going to be a cosine, which is going to be a cotangent of theta. And cosine times secant is going to be a 1. Maybe I should have done by sine. Yeah, I should have done by sine, but whatever. I already picked cosine. So if I do cosine times secant, that's going to be a 1. And then this would be, again, remember, cosecant, ladies and gentlemen, is 1 over sine, right? So actually, let me just rewrite those. So if I rewrite this as 1 over cosine of theta minus a 1 over sine of theta divided by a 1 over a cosine of theta plus a 1 over sine of theta. You know what? Forget that. Why am I doing this with cosines? That doesn't make any sense. I want to create a tangent. Tangent is sine over cosine, right? So I want to multiply everything by a sine of theta. So let's do a sine of theta times a sine of theta. Because if I do that, what's going to happen when I multiply by a sine of theta in the numerator as well as in the denominator, that's going to create a tangent, that's going to create a tangent, that's going to go to 1, and that's go to 1, and that's exactly what I'm looking for. So I don't know why I thought cosine. So sine over cosine, that's going to be a tangent of theta. Sine of theta times a 1 over sine is going to be a minus 1. Then over here, I have a tangent of theta. And sine of theta times 1 over sine is going to be a positive 1. And voila, that actually wasn't that much work at all. All right, the next one. So here I have tangent of alpha plus secant of alpha. A couple different ways we could go about this. I am thinking that in this problem, I'm going to rewrite this in terms of sines and cosines. That's going to create a fraction, which then I can maybe get a common denominator that will be a 1 minus a sine of alpha. So let's just try it. So if I have sine of alpha, that's going to be a sine of alpha over a cosine of alpha plus a secant, which would be a 1 over a cosine of alpha. All right, that already has common denominators, so that's good. So therefore I can do a sine of alpha plus 1 over a cosine of alpha. And I guess I just could have rationalized the denominator. It would have gotten the yeah, you know what? I could have created this and gotten rid of it. Let's actually try that. Well, yeah, because then you're going to want to multiply by the conjugate again. So why go through all that work? Sorry, guys, I have some experience with this. So in this case, you could do it that way. And if we don't get the right answer, then I'll do it this way. But I'm thinking here, I want to multiply by the conjugate because I want to get rid of my this binomial fraction. So I'm going to multiply by the conjugate, which is a 1 plus a sine of theta. And remember, just like we did in the beginning, when you multiply by a conjugate, that creates a difference of 2 squares. So up top, we have cosine of alpha times 1 plus sine of alpha. I'm just going to leave that where it is. Not going to distribute it just yet. And then over here, this is going to give me a 1 minus a sine squared of alpha. Now remember, ladies and gentlemen, that is equivalent to a cosine, right? Or a cosine squared. So I have a cosine of alpha times a 1 plus a sine of alpha, and that's going to be divided by a cosine squared of alpha. Now remember, cosine squared is cosine times cosine, right? So I can divide out this cosine with one of those cosines. Now I'm going to have one cosine left in my denominator, which, just like I did, where was it? Up here, you got to make sure you divide into both those terms since they're separated by subtraction. I think I have enough room, so maybe I'll show it. So now I have a 1 plus a sine of alpha divided by a cosine of alpha. Divide that into both those terms. I get a 1 over a cosine of alpha, or theta, plus a sine of theta divided by cosine of theta, which, ladies and gentlemen, we know that's going to be a secant of theta, and sine over cosine equals a tangent of theta, which exactly works. Voila. So that one works perfectly fine in that case as well. All right. So now the next one, so that comes into rationalizing the denominator. This next one, I see something squared, so I immediately think Pythagorean identities. And remember, guys, cosine of theta, cosine squared of theta plus a sine squared of theta is equal to 1. So in this case, if I want to know what cosine squared of beta minus 1 would be, I would have to subtract the 1, and then I'd have to subtract the sine squared over there. So this is going to be equivalent. So let's do this. A cosine squared of theta minus 1 is equal to a negative sine squared of theta. Now, again, I'm using theta and the problem's with beta, but you don't always have to like switch everything around. So this is going to be a negative sine squared of beta divided by a cosine of beta. All right. Now, again, sine squared is 2 of them, right? So we have a negative sine. I don't want to do sine squared. New negative sine of theta times a sine of theta all over a cosine of theta. Why am I doing thetas? Mr. McLogan, you're getting yourself confused. That's a sine of beta times a sine of beta divided by a cosine of beta. Which again, ladies and gentlemen, I can group these since they're separated by multiplication, right? I only need to divide them into one of them. And now, ladies and gentlemen, what I'll have is that becomes a negative tangent of beta times a sine of beta. And you can see that's exactly what we were looking for. Voila. All right, the next one. So in this case, in this one, what could I do to get my sines and cosines? All right. So this one in terms of sines and cosine, this one's not. I don't really like that. So what I'm going to do is I'm going to rewrite this as a 1 over a cosine. Let's just rewrite the problem. So in this case, I can rewrite this as a 1 over a cosine of x plus 1 all over a sine of x over cosine of x. All right, one thing I noticed, guys, is I have cosine in the denominator, in the top and the bottom. I don't want cosine in the denominator. So first thing we're going to do is going to multiply by a cosine of x on the top and on the bottom. When doing that, make sure you put parentheses around here. I actually almost made the mistake. So therefore, that's going to be a 1 plus a cosine of x, and those are going to divide out, divided by a sine of x. Okay. Now again, we want this to equal a negative cosine of x. So in this case, so again, kind of like what we did over here is I want to create a perfect square trinomial, or I want to multiply by the conjugate because then I know 1 minus cosine squared, or 1 squared minus cosine squared, I can rewrite as a sine squared. So if I go ahead and take this, multiply by the conjugate, which would be 1 minus a cosine of x times a 1 minus a cosine of x. That's going to give me a 1 minus cosine squared. Oh man, we're running out of room here. So it'll be 1 minus cosine squared of x. And that's going to be times a 1 minus cosine of x times a sine of x. Okay, now what do we know about 1 minus cosine of x? So if I took cosine squared, subtracting both sides, that's equal to a sine squared, right? And so that's going to be equal to a sine squared. Sine squared divided by sine is just going to be a sine. So therefore, I'm going to be left with a sine 1 minus a cosine of x. Where am I getting the negative? Where'd the negative come from? That's going to be 1 minus cosine squared. Oh, sorry, I forgot about that. Yeah, it'd be a 1 minus, yeah, a 1 minus cosine squared. 1 minus cosine squared. So how am I getting the squared, sine squared, minus cosine? So that's incorrect. I think I wrote that wrong. That's incorrect. Because 1 minus cosine squared is just going to be a sine squared, right? And so you have a sine squared. So you have a sine, so that's equal to now to, let's go through this. So that's now equal to a sine squared of x. And now I have two sines, right? Sine squared, sine times sine. So one of those will divide out. So we'll use black for that. So that can divide out, and that will divide out. And that's going to leave me with my final answer, which is supposed to be a sine of x divided by a 1 minus a cosine of x. So I think I wrote that problem wrong. So I'll make sure that's fixed for you guys. All right. Whew, I told you there's a lot of examples. But ladies and gentlemen, the more examples you do, the better and better and better you are going to get. All right. I think another rationalizing the denominator problem. If I want to get rid of this and put this in the denominator, again, go ahead and rationalize the denominator. So let's go ahead and multiply by a 1 plus 1. Oh, geez, that looks horrible. So multiply by a 1 plus cosine of y, 1 plus cosine of y. That's going to give me a 1 minus cosine squared of y. Is that the exact same problem? Pretty much. That's kind of funny. It's like the exact same problem. So I'll just figure it in there. I might add a different one. So sine of y times a 1 plus cosine of y. And that becomes a sine squared of y all over a sine of y times a 1 plus a cosine of y. And again, those are going to divide out. So you're left with a sine of y over 1 plus cosine of y. I don't know why I make this out there. I'm probably going to change this one out. So therefore, my final answer is a sine of y all over a 1 plus cosine of y. I don't remember, but remember, these are my notes that I took from the classroom that I had, and I'm reworking, going back through from there. So I'm not sure why I kept both of those in there or why I made that mistake from there, but you probably got the updated version on that case. All right, let's go and take a look at this one. So here I have two fractions that I got to combine. I think the easiest thing for us to be able to do in this case would be to get common denominators. So to get common denominators, you can see that like a lot of times students have trouble with common denominators, even with numbers. But actually, when you're dealing with polynomials or trig functions, it's pretty simple. Like the product more likely than not is going to be the common denominator. Obviously, sometimes one is a factor of another. But in this case, the easiest thing to do to get common denominator is just to multiply by the product of each one. So we have a sine of theta. I'll multiply over here. And then over here, I'll multiply by a 1 plus a cosine. My computer is not liking that. Cosine of theta. And multiply by 1 plus a cosine of theta. Okay. So this is going to be a sine squared. Now over here, this is going to be a binomial squared. So that's going to create a perfect square trinomial, which would be a 1 plus 2 cosine of theta plus a cosine squared. I don't have a lot of room, but if you want to multiply it out on your own, like using FOIL, then by all means, go ahead and do that. Since we multiply to get common denominators, we know that they're going to be over the common denominator. So I just simplified both the numerators, put them over the same one, which is going to be a sine of theta times a 1 plus cosine of theta. Okay, now a couple things I recognize here is that, hey, I have a sine squared plus cosine squared, right? Sine squared plus cosine squared we know is equal to a 1. And then, so that's equal to a 1, and then I can do 1 plus 1, which is going to be a 2. So in my numerator, I can simplify this to a 2 plus 2 cosine of theta, and that's all over a sine of theta times a 1 plus cosine of theta. Which, ladies and gentlemen, I can now factor out my 2, and if I factored out the 2 here, I'd be left with a 1 plus a cosine of theta. Right? So if I read in this factored form, now what I want you guys to see is I have a 1 plus cosine of theta in the numerator, a 1 plus cosine of theta in the denominator. Those are going to divide out. So now I'm going to be left with a 2 over a sine of theta, which is equal to a 2 cosecant of theta. And now that has been verified. How many more we got? I forgot. Okay. 1, 2, 3, 4, 5, 6. 6 more. All right. Next one. So in this case, we have 1 over tangent plus tangent equals secant squared of theta over tangent squared. So I think it's a lot easier to go ahead and combine these. So let's go ahead and combine our fractions over here. So if I put this over 1, then remember to get common denominator, I can multiply by a tangent of theta over a tangent of theta. So therefore, I'm going to have a 1 plus a tangent squared of theta all over a tangent of theta. Okay, now one thing we didn't talk about is the other trigonometric identities, right? We have sine squared plus cosine squared equals 1. And just remember, we also have 1 plus a tangent squared is equal to a secant squared. Wrong one. That's equal to a secant squared of theta. And then also the other one is going to be a cotangent squared of theta plus 1 is equal to a cosecant squared of theta. Okay, so remember also those two trigonometric identities. So 1 plus tangent squared of theta, we know it's equal to secant squared. So in this case, we have a secant squared of theta divided by a tangent of theta. And voila, ladies and gentlemen, we are good. Next one, 1 over secant of beta divided by tangent of beta. So we have a reciprocal on both of these. In this case, well, it kind of looks like I can recreate these two. 1 over a tangent of beta. Let's go and work on this right-hand side. Let's convert things to sines and cosines and see what we get. So I have a 1 over a sine of beta minus a sine of beta. Put that over 1. Let's go ahead and multiply by the sine of beta on both sides. So now that's going to give me 1 over a sine of beta. That's actually my common denominator. And this would be a 1 minus a sine squared of beta. So remember, that's going to be equal to a cosecant square or cosine squared. So that's a cosine of beta divided by a sine of beta. And cosine over sine of beta. And then I can rewrite this. I can divide the sine with one of them, right? Because remember, that's cosine of beta times cosine of beta divided by a sine of beta, which we could group those two together. And that's now going to leave me with a cosine of beta times cosine over sine, which is going to be a cotangent of beta, which, ladies and gentlemen, you can see is actually the reciprocal of 1 over secant. So I can rewrite this as 1 over a secant of beta and times a 1 over the reciprocal of that would be a tangent of beta. So you can see actually that works working over there on the right-hand side. Next one, we go to secant and secant of x minus cosine of x. Again, kind of looking into the same idea here. If I have secant, I can rewrite that as a 1 over a cosine of x minus a cosine of x over 1. Again, get common denominators. So we'll multiply by a cosine of x, cosine of x. So that's going to be 1 minus a cosine squared of x divided by a cosine of x. 1 minus cosine squared of x, that's going to equal a sine squared. So again, I have a sine squared of x divided by cosine of x. And again, remember that is the same thing as sine of x times sine of x all over cosine of x. You can group those together. So by grouping these together, sine over cosine equals a tangent. And then we have a sine of x times a tangent of x. And voila. Next one is cofunction identity. So we need to know how to rewrite this cofunction identity. So tangent of pi halves minus theta, that's going to be rewritten as cotangent of theta. Why am I writing this in gray? Go back to red. So this can be rewritten as a cotangent of theta times a tangent of theta. And hopefully you recognize cotangent times tangent. They're reciprocals of each other. So that's just equal to a 1. All right, last 2 examples, ladies and gentlemen. So in this one is we have cosine of 4th minus sine squared. Okay, so if I have something to the 4th power and I want to break it down into something squared, one thing I can do here is I can apply the difference of 2 squares, right? So I can rewrite this as a cosine squared minus a sine squared. Let's see, these are all of x, times a cosine squared of x plus a sine squared of x. Now, what do we again remember about cosine squared plus sine squared? That's equal to 1. So I'm just going to be left with a cosine of x minus a sine squared of x, which is exactly what we're looking for here on the right-hand side. Now, in this next example, can't really do that, but I do recognize that over here I have common factors, right? They both have a sine, so I could factor out a sine squared of alpha. By factoring out a sine squared of alpha, I'm left with a 1 minus a sine squared of alpha. 1 minus sine squared of alpha. Then, if I need to get everything in terms of cosines, with my Pythagorean identities, I know I can rewrite. That's incorrect. That's one of those is supposed to be to the 4th power. I'll figure out which one is. So sine squared of alpha times 1 minus a sine squared of alpha. I can rewrite these in terms of cosines, right? Using my Pythagorean identity. So sine squared, I can rewrite as a 1 minus a cosine squared of alpha, and 1 minus sine squared of alpha, I can rewrite as a cosine squared of alpha. Now, applying distributive property again, I get a cosine squared of alpha minus a cosine to the 4th of alpha, which is exactly what I was looking for. So, there you go, ladies and gentlemen. Now, I know these are not all the different types of identities, but this was a lot, and we covered a lot in this lesson. And I hope that you have a good foundation and guidance on how to approach verifying identities, but in reality, you're going to need more examples. So I want to make sure I can provide more practice to you. So therefore you have that in store. So I'll make sure I have these notes as well as more practice examples for you to be able to download down below. Make sure you go ahead and do that before we get into the next lesson. Cheers.